Welcome. You have nothing left to do tonight, nowhere to be, nothing to solve, no decisions left to make. Let your shoulders settle. Let your hands rest open. You are here, in the dark, and the only thing asked of you now is to breathe and drift. Tonight we trace a quiet, vast journey, the long, unhurried story of the moon, and where time will slowly carry it over the next 1 billion years. Let that span wash over you like a tide, warm and wide. The moon formed approximately 4.5 billion years ago from a giant impact, one of the most immense events in the history of our solar system. A young Earth, still half molten and formless, received a collision so vast it reshaped everything. From that single catastrophic moment, our familiar companion was born. The moon did not wander in from elsewhere, and it did not simply condense alongside the Earth. It was forged from Earth itself, in fire and debris, long before any ocean ever gathered. A Mars-sized body called Theia collided with the early Earth in that ancient moment. Theia was a planet in its own right, rocky, dense, probably formed in one of the gravitational equilibrium points along Earth's own orbit. Over millions of years, subtle tugs from Jupiter and Saturn nudged Theia off course. It drifted, very slowly, onto a path that intersected with Earth. The collision was not quick or sharp like a struck match. It was a slow, grinding planetary embrace that lasted hours. The Theia impact ejected a ring of molten debris into Earth's orbit, spreading outward in a vast arc of superheated rock and vapor. The collision punched material from both Theia and Earth's own mantle into space simultaneously. That material did not simply float away into the solar system. Gravity held it in a wide, churning disk around the wounded Earth, glowing orange and red against the black. The ring was enormous, stretching tens of thousands of kilometers in every direction. That debris ring coalesced into the moon within roughly 1,000 years, an eye blink in cosmic time. Pieces of molten rock drifted together, drawn by their own modest gravity, colliding and merging without violence. Each small merger added to the growing mass. The process was not chaotic, but self-organizing, the way a raindrop gathers from smaller droplets. Within 1,000 years, which is almost nothing against the 4.5 billion years that followed, a new world had assembled itself from the ruins of the impact. The early moon orbited Earth at only about 24,000 kilometers distance, strikingly close by any measure. Today, the moon rests roughly 384,000 kilometers away. But in those first ancient days, it hung in Earth's sky as an immense luminous sphere, vastly larger and more brilliant than the moon we know. Its gravitational pull on the young Earth was correspondingly powerful, raising enormous tides in the oceans of molten rock below. The sky and the ground were inseparable from each other then. Earth's early day lasted only 6 hours due to the planet's rapid rotation. The same impact that formed the moon spun Earth faster than it had ever turned. A full sunrise to sunrise cycle compressed into a single short stretch, the sun crossing the sky 4 times in what we now call a day. The rapid spin meant violent atmospheric circulation, enormous tidal forces, and a world that barely paused between morning and night. Everything about that early Earth moved with a kind of breathless, churning energy that has since settled, very gradually, into stillness. The moon was once covered entirely by a global magma ocean, a world of nothing but glowing, churning rock in every direction. No highlands, no craters, no maria, just an unbroken surface of incandescent liquid minerals, slowly swirling under the pull of Earth close above. The heat was both its own, retained from formation, and fed by the constant flux of tidal energy from Earth. At that moment, the moon was not the quiet silver companion we know. It was an ocean of fire suspended in orbit. The lunar magma ocean took roughly 200 million years to fully solidify. That cooling was unhurried on a human scale, but relentless. As surface layers lost heat to the vacuum of space, they thickened from the outside inward, like the skin forming on still water on a cold night. Below that growing crust, convection currents carried heat upward. Minerals crystallized from the melt, each at its own temperature, separating like ingredients settling in a jar of still liquid. 200 million years of patient cooling, and then the moon had a surface. Denser minerals sank to form the lunar mantle during solidification. As the magma ocean cooled, minerals rich in iron and magnesium crystallized early and fell inward under their own weight, gathering into the deep interior. The mantle built up layer by layer from below, each generation of crystals settling quietly into place. This was differentiation, the same process that gave Earth its iron core, its rocky mantle, its thin crust. The moon did it too, in its own slower, quieter way. Below the surface, you can see, a layered world was assembling itself in silence. Let the breath come and go without any effort from you. Breathe in and allow the exhale to lengthen just a little, longer than the inhale, trailing off like the last note of a song fading into a room. There is no pace to keep, no direction to follow. Each breath carries you a little further from the day, a little deeper into rest. The exhale does the work. You only receive it. As the magma ocean finished cooling, the moon organized itself into 3 distinct layers: a crust, a mantle beneath it, and at the very center, a small iron core. This is the same architecture that Earth carries, and that most of the rocky worlds in the inner solar system share. Gravity had done its patient sorting, pulling the heaviest elements inward and leaving the lightest at the surface. A world with structure, with depth. The moon was no longer a uniform ball of cooling rock. It had become a layered place. At the heart of the moon, that iron core stretches about 330 kilometers in radius, a sphere of metal smaller than many countries on Earth, compressed under the weight of everything above it. By comparison, Earth's core reaches over 3,000 kilometers outward. The moon's is modest, almost small enough to seem accidental, yet it was enough once to generate a magnetic field, enough to leave a signature in the rocks that scientists can still read today, billions of years after the core fell silent. Between 4.1 and 3.8 billion years ago, a period known as the Late Heavy Bombardment descended on the inner solar system. Both Earth and Moon were battered by an intense wave of asteroids and comets, a rain of rock and ice from the outer reaches of the solar system, drawn inward by the shifting orbits of the giant planets. The Moon, with no atmosphere to cushion the blows, received each impact directly. Crater upon crater accumulated across its surface during those 300 million years, and the record of that time is still written plainly on the face we see tonight. The largest of those ancient collisions did not leave simple craters. They excavated enormous hollows, basins hundreds of kilometers across, gouged deep into the crust by objects the size of small cities. Planetary scientists have concluded that these basins formed during the peak of the bombardment, when impactors were still large enough to reshape the moon's entire landscape in a single event. The shock of each impact rippled through the crust, lifted mountains along the basin rim, and left a permanent scar that no wind or rain would ever erode away. Near the moon's south pole lies one of the most impressive scars in the entire solar system. The South Pole Aitken Basin spans roughly 2,500 kilometers across and plunges nearly 8 kilometers deep, a wound in the crust so vast that it is difficult to perceive even from orbit. It is among the oldest impact structures known, formed during the earliest chapters of the bombardment. Standing at its center, you would see a horizon that curves away in every direction, ringed by distant mountains of ancient crustal rock, the floor of the basin darker and quieter than almost anywhere else on the moon. Volcanic eruptions then reshaped much of what the bombardment had broken. Between roughly 3 and 4 billion years ago, magma forced its way up through cracks in the thinned and fractured crust, pooling into the Great Basins and flooding them with dark basalt lava. These eruptions were not explosive. They were broad, spreading flows, more like the lava fields of Hawaii than the explosive cones we picture on Earth. Layer after layer of dark basaltic rock built up across the basin floors, filling the low points and smoothing what had been rough and shattered terrain into broad, flat plains. Those dark volcanic plains are what give the full moon its familiar face. The lighter regions are the ancient highlands, scarred with craters. The darker patches are the solidified basalt, and arranged together, they sketch out the rough shape of a face, or a rabbit, or a frog, depending on who is looking. Cultures around the world have seen different figures in the same pattern, but all of them are reading the same geology. Ancient volcanic flows resting in ancient impact basins, preserved without change for billions of years. Volcanic activity on the moon did not end abruptly. It wound down, gradually, as the interior cooled and the supply of molten rock diminished. By about 1 billion years ago, eruptions had essentially ceased. The last flows were thin and sparse compared to the great floods of the earlier era. Geologists who study returned lunar samples have dated lava flows as young as 1 billion years, placing them much closer to the present than most of the moon's volcanic history. After that, the moon became what it is now, a geologically finished world, its surface no longer changing from within. From the very beginning, 4.5 billion years ago, tidal forces between Earth and the moon had been exchanging angular momentum, the physical quantity that describes how much spin and orbital motion a system carries. Not a single rotation of Earth, not a single orbit of the moon has passed without this exchange occurring. The moon pulls on Earth's tidal bulge, and Earth pulls back on the moon. Energy flows between them like a current between 2 points. This exchange has never paused, never reversed. It is the most patient negotiation in the history of our solar system. Angular momentum, the total spinning and orbiting energy of the Earth-Moon system combined, is conserved. No matter how the two bodies exchange energy between themselves, the sum never disappears. It only moves from Earth's spin to the moon's orbit, from the moon's orbit back to Earth's rotation, shifting in form but never diminishing in total. This is one of the deepest rules of physics, and the Earth and Moon have been obeying it faithfully for 4.5 billion years, without a single exception. Let your body grow heavy now. Feel the weight of your arms resting against the mattress, not held up, not tense, just settled. Notice how your shoulders have dropped. Your hips, your legs, your feet, each one pressing down into the warmth beneath you. You do not need to hold yourself up. The surface beneath you is holding you completely. Breathe out slowly. Let each breath release a little more weight. You are not floating. You are held fully and completely, sinking deeper into stillness with every exhale. Tidal bulges on Earth are raised by the moon's gravitational pull. The moon does not pull on all parts of Earth equally. The side of Earth facing the moon is pulled more strongly than the center, and the center more than the far side. This difference in pull stretches Earth ever so slightly along the line, pointing toward the moon. The oceans, being fluid, respond most visibly, rising in a broad, low dome on the near side, and in a corresponding dome on the far side. The solid rock of Earth also bulges, though far less dramatically than the water above it. Earth's rotation carries those tidal bulges slightly ahead of the moon's position. This happens because the solid Earth spins faster than the moon orbits. The bulge that the moon raises does not sit directly beneath the moon. Earth's rotation drags it forward, like a wave slightly ahead of the stone that created it. The result is a persistent misalignment. The two tidal humps lean a few degrees ahead of the moon's current location at all times. It is a small offset, barely noticeable, yet it is the engine driving everything that follows in the long story of the moon's drift. That offset bulge exerts a gravitational torque that pulls the moon forward in its orbit. Because the leading tidal bulge sits slightly ahead of the moon, its gravitational attraction tugs the moon in the forward direction, the direction the moon is already traveling. It is a gentle nudge, repeated endlessly on every orbit, in every year, in every era. Physics calls this a torque, a force that does not simply push but twists, adding to the moon's orbital motion rather than fighting it. The same small nudge that barely registers in a single year accumulates, over billions of years, into something enormous. The forward pull accelerates the moon, which causes it to rise into a higher orbit, spiraling outward from Earth. This seems backward at first. Accelerating an orbiting body does not make it go faster in the way we expect. Instead, orbital mechanics dictates that the added energy lifts the moon to a larger orbit, where it actually moves more slowly than before. The moon gains energy, yet slows down. This counterintuitive dance is real, verified, and measurable. The moon has been drifting outward this way for billions of years, and it continues to drift outward today. Right now, at this moment in the moon's long history, it recedes from Earth at approximately 3.8 centimeters per year. That is about the rate at which fingernails grow. Over a human lifetime, the moon moves away by less than 3 meters. Over a century, less than 4 meters. The number is small enough to seem trivial, yet multiplied across a billion years, it adds up to tens of thousands of kilometers. The moon is leaving unhurriedly, 1 year at a time, 1 quiet centimeter at a time. Apollo astronauts placed laser retroflectors on the moon to measure this recession with precision. These devices, flat panels lined with corner cube prisms, were left on the lunar surface during the Apollo 11, 14, and 15 missions. A laser pulse fired from Earth bounces off the panel and returns. By timing the round trip to within a fraction of a nanosecond, scientists can calculate the exact distance to the moon. Each measurement is precise to within a few millimeters. The retroreflectors still sit there on the surface, waiting patiently for the next laser pulse from Earth. Lunar laser ranging experiments have tracked the moon's gradual drift with millimeter accuracy since 1969. Over more than 50 years of measurements, observatories around the world have fired laser pulses at the moon and recorded the returning light. The accumulated data form one of the most precise long baseline measurements in all of science. The trend is unmistakable. The moon is moving away. The data show not just the average recession, but seasonal variations, wobbles in the moon's orbit, and even tiny shifts caused by tides in Earth's solid crust. Earth loses rotational energy to tidal friction as the moon recedes. The tidal bulges raised by the moon are not frictionless. Ocean water rushing across shallow seafloors, sloshing against coastlines, pressing against the edges of continents. All of this generates heat. That heat comes from somewhere. It drains from Earth's rotation. Each day, Earth spins a fraction of a heartbeat slower than the day before. The energy does not vanish. It transfers outward, carried into the moon's growing orbit. Earth gives up its spin, and the moon rises a little higher in return. Earth's day is currently lengthening by about 1.4 milliseconds per century. That number, 1.4 milliseconds, is nearly imperceptible. A blink of an eye takes roughly 150 milliseconds. 1.4 is a fraction of that. Yet century by century, the day accumulates a little more length. Over 1 million years, this adds up to about 14 seconds. Over 1 billion years, the day grows by hours. Time itself, the rhythm of morning and night, is not fixed. It stretches, barely but steadily, like a breath held just a little longer each time. Shallow seas are responsible for a surprisingly large share of Earth's rotational energy loss. As ocean tides roll across continental shelves, those broad submerged ledges ringing the continents, water churns against the seafloor in long, sweeping friction. The energy bled away in these shallow regions dwarfs what is lost in the deep ocean basins. The Persian Gulf, the Bering Sea, the waters off Patagonia, each one a site where the turning of the earth is quietly taxed, millimeter by millimeter, tide by tide, century by century. Somewhere far off, there is a sound, not quite a hum, not quite wind. It rises at the edge of hearing, holds for a moment, then fades back into the dark. The house shifts. A beam settles. The sound comes again, low and unhurried, and then recedes once more. Your body knows this rhythm. Your shoulders have already dropped. The air is still. Each small sound that surfaces only deepens the surrounding hush when it is gone, and the hush holds you, and the hush is enough. Ancient coral fossils reveal that Earth once had about 400 days in a single year, roughly 400 million years ago. Corals, like trees, lay down growth rings, daily bands, and annual cycles recorded in their calcium carbonate skeletons. Paleontologists, counting these microscopic bands in fossilized specimens, found something extraordinary. There were more daily rings per annual layer than in corals living today. The year had not shortened. The days had. Each day was briefer, the Earth spinning faster then and the moon riding closer, pulling harder on those shallow ancient seas. Tidal rhythmites, preserved in ancient rock strata, also carry a record of Earth's rotational history. These are layers of fine sediment deposited by tides, alternating bands of coarser and finer material, each one corresponding to a tidal cycle. Where the layers are well preserved and carefully counted, they act as a calendar written in stone. Geologist George Williams studied rhythmites in South Australia in the 1990s and found evidence that 700 million years ago, the lunar month lasted only about 22 days. The rocks had been listening to the moon long before any living creature had ears. The moon's recession rate was faster in the deep past, when tidal forces between Earth and moon were considerably stronger. When the moon was closer, its gravitational pull raised taller tides. Taller tides meant more energy flowing through shallow seas. More energy dissipated meant a swifter transfer of angular momentum outward, and so the moon pulled away faster than it does now. The recession we measure today, 3.8 centimeters per year, is actually a slower pace than the average over the moon's full history. The system has been losing urgency as it ages. During periods when supercontinents dominated Earth's surface, the moon receded most slowly. A supercontinent, a single vast landmass covering much of the globe, leaves relatively little room for broad, shallow continental shelves. Deep ocean basins, while vast, dissipate far less tidal energy than shallow coastal waters. Geophysicists studying this pattern have concluded that each time continents merged into a supercontinent, the engine of tidal dissipation ran at lower power. The moon's outward drift slowed accordingly, as though the planet were briefly holding its breath. Earth's continents shape tidal dissipation by changing the geometry of ocean basins. An ocean enclosed or narrowed by land resonates differently from an open one. When a basin's natural resonant frequency happens to match the tidal forcing frequency, dissipation surges. When continents drift and basins change shape, that resonance shifts. Oceanographers have modeled how continental configurations millions of years in the past produced dramatically different tidal amplitudes. The arrangement of land masses is, in this sense, a kind of instrument, and over geologic time, it plays a slow changing tune that the moon must follow. Tidal dissipation rates have varied considerably across the span of Earth's history, rising and falling with the geography of continents and the depth of seas. This means the moon's recession has not been a smooth, steady drift outward. It has been uneven, faster in some eras, slower in others, sometimes briefly plateauing as tectonic conditions shifted. Reconstructing this history is painstaking work. Researchers piece it together from fossil rhythmites, ancient corals, and computer models of vanished ocean basins. The result is a biography of the Moon's departure, written in stone and water over 4 billion years. Milankovitch cycles, the long rhythmic variations in Earth's orbit and axial tilt that drive ice ages, are partly shaped by the Moon's orbital distance and its influence on Earth's tilt. The Serbian mathematician Milutin Milankovitch, working in the early 20th century, calculated how small changes in Earth's orbit around the Sun alter the distribution of sunlight across the globe. What he could not fully account for is that the Moon acts as a stabilizer, moderating how much Earth's tilt wanders over time. As the Moon recedes across the coming ages, its stabilizing influence will gradually lessen, and Milankovitch cycles themselves may slowly begin to shift. Earth's axial tilt, the angle at which our planet leans as it travels around the Sun, stays remarkably steady, held within about 2.4 degrees of its current position over millions of years. That steadiness is the Moon's quiet work. Its gravitational presence counteracts the subtle tugs of Jupiter and Saturn, which would otherwise nudge Earth's axis into wandering. The result is a world whose polar regions and equator receive predictable amounts of sunlight, era after era, and whose seasons return with reassuring regularity. Without the Moon, Earth's axial tilt could drift anywhere between 0 and 85 degrees over millions of years. A planet leaning at 85 degrees would have its poles pointing almost directly at the Sun, one hemisphere baked for half a year, then plunged into absolute darkness. Near 0 degrees, the seasons would nearly vanish. A French dynamicist named Jacques Lascar, working in the 1990s, modeled this possibility and found the resulting climate swings would be extreme. The Moon, simply by being there, shields the planet from that lurching instability. Mars offers a glimpse of what a moonless Earth might have endured. Its two moons, Phobos and Deimos, are tiny, captured asteroids with far too little mass to stabilize anything. Over millions of years, Mars's axial tilt has swung dramatically, perhaps as low as 10 degrees and as high as 60 degrees or more. Jacques Lascar's team found that this wandering has shaped the red planet's climate in profound ways, shifting where ice accumulates and how its thin atmosphere behaves. Mars is, in a sense, a natural experiment, a rocky world without a steady hand on its axis. Warmth is spreading through your hands now, rising from your palms, up through your wrists, settling into your forearms. Your shoulders are letting go of something they did not need to carry. Down through your back, warmth gathers at the base of your spine and fans outward. Your legs are heavy. Your feet are still. Each breath draws warmth in and lets the last of the day out. There is nothing left to tend to. The warmth is doing the tending now. You are held. You are unhurried. You are easing down. The Moon's steadying of Earth's axial tilt has been one of the most consequential forces in planetary history. A stable tilt means stable seasons. Stable seasons mean stable temperatures across large regions of Earth, season after season, millennium after millennium. Climate scientists studying the deep past have traced how that consistency allowed soils to deepen, carbon cycles to run reliably, and ocean currents to establish long-lasting patterns. The Moon did not create life, but it maintained the conditions in which life could persist long enough to grow truly complex. Complex life on Earth required not just a suitable planet, but an extraordinarily long span of stable conditions. Hundreds of millions of years of manageable temperatures, persistent oceans, and reliable seasons. The Cambrian explosion of animal life occurred about 540 million years ago, and the lineages it sparked have persisted through countless generations, precisely because the world did not tilt into catastrophe. The axial stability the moon provides is easy to overlook, woven into the background of every ecosystem that has ever existed. It is the frame inside which all of Earth's biological richness was quietly built. The moon completes one full orbit around Earth in 27.3 days. Astronomers call this the sidereal month, measured against the fixed background of distant stars rather than against the sun. That rhythm has been ticking reliably for billions of years. 27 days, 8 hours, and a handful of minutes. It is long enough that casual observers rarely notice the moon returning to the same position among the stars. Yet that cycle underpins the tides, the calendars, and the long-term dance of angular momentum between Earth and its companion. The moon always shows the same face to Earth: the dark volcanic plains, the bright highlands, the ghostly glow of the full moon. All of it is one side, the near side, turned perpetually toward us. The moon's far side, which remained entirely unknown until a Soviet spacecraft photographed it in 1959, is a different-looking landscape, more cratered, with fewer of the dark volcanic basins. This locked posture is not coincidence. It is the end state of a long mechanical process, gravity having wound the moon down into a perfectly synchronized relationship with our world. Billions of years ago, the moon rotated much faster, spinning through its own days independently of Earth. Tidal forces, the same gravitational stretching that raises the oceans, acted on the moon's solid body, creating a slow friction. Over enormous spans of time, that friction bled away the moon's rotational energy. Spin by spin, era by era, the rotation slowed. Eventually, it matched the orbital period exactly. At that moment, synchronous rotation was achieved. The moon settled into a posture it has held ever since, facing Earth with the same expression across all of human history. Tidal locking is not unique to the moon. It occurs wherever one body orbits another, closely enough that tidal forces have time to do their work. The process begins when the tidal bulge raised on a rotating body is carried out of alignment with the line connecting the two objects. Gravity pulls on that misaligned bulge, creating a torque. The torque acts as a brake. Over time, sometimes millions of years, sometimes billions, the rotation slows until the body turns exactly once for every orbit it completes. It is an inevitability. Given enough time and proximity, gravity always wins this particular negotiation. Earth itself is being drawn, ever so gradually, toward the same fate the moon long ago completed. The moon's tidal forces work on Earth's oceans and solid body, creating that same slow mechanical brake that once wound down the moon's own spin. Earth is losing rotation. Day by day, century by century, the process is underway. But Earth is far more massive, and the moon, though a capable sculptor, has far less leverage over its larger partner. Calculations suggest the full tidal locking of Earth toward the moon would require far longer than the sun itself will last. A perfectly circular orbit is rare in nature. The moon's path around Earth is an ellipse, not dramatically stretched, but measurably so. Its eccentricity sits at about 0.055, a small but real departure from a circle. At its closest approach, called perigee, the moon is roughly 30,000 kilometers nearer to Earth than at apogee, its farthest point. That difference is enough to make the moon appear subtly larger and brighter at perigee. Ancient sky watchers noticed the moon's changing face. They simply had no mathematics yet to name what they saw. Orbits rarely sit flat against the same plane as everything else. The moon's orbital path is tilted, inclined about 5.1 degrees, relative to the ecliptic, the plane along which Earth travels around the sun. This modest tilt is enough to send the moon above and below the ecliptic each month, like a coin rolling at a slight angle around a table. Because of this inclination, the moon does not cross the sun's apparent path in the sky every orbit. Eclipses only happen when the geometry aligns, when moon, earth, and sun all share a precise narrow meeting. Precession is the slow wobble of an orbit's orientation, and the moon's orbital plane traces this cycle over 18.6 years. The 2 points where the moon's orbit crosses the ecliptic, called the nodes, drift westward around the sky like hands on a vast celestial clock, completing one full circuit in that 18.5-year span. Navigation charts, eclipse prediction tables, and tide tables have all encoded this rhythm for centuries. Chinese astronomers tracked it. Babylonian scribes noted it. The cycle was old knowledge long before anyone knew the geometry beneath it. Let the breath come on its own now. No need to guide it. Somewhere far above, an ember of light dims in the eastern sky, a late star fading as morning draws near somewhere else entirely, while here the dark holds. The body has already been settling, bit by bit, the shoulders slack, the jaw eased, the hands loose where they rest. There is no effort required now. The mind can release the last shape of the day, like a thread let fall from open fingers, drifting, thinning, dissolving into the dim and quiet warmth of the room. That 18.6-year cycle of the lunar nodes leaves a fingerprint on Earth itself. As the nodes shift, the moon's pull on the oceans changes in subtle ways. High tides run a little higher, then a little lower over the course of the cycle. Researchers studying long-term tide gauge records have found this periodicity woven into the data like a slow heartbeat. More striking still, climate scientists have found echoes of the cycle in regional precipitation patterns and sea surface temperatures in certain parts of the world. The moon reaches down through gravity and touches even the rainfall. Total solar eclipses happen because of a coincidence so precise it borders on the improbable. The sun is about 400 times wider than the moon, but also about 400 times farther away. Those two ratios nearly cancel, leaving the moon and the sun with almost identical apparent diameters as seen from Earth's surface. When alignment is exact, the moon's disk slides over the sun's disk and covers it almost perfectly, revealing the corona, the sun's outer atmosphere, a pearly white halo that is otherwise invisible. No other planet in the solar system has a moon that fits its sun so neatly. This near-perfect size match is not a permanent feature of the cosmos. It is a window, one that happens to be open during the age of human existence. The moon is receding. The sun is not. As the moon drifts outward over millions and billions of years, its apparent size will shrink. The coincidence of matched diameters is being slowly undone. We exist, as it happens, during the narrow span of Earth's history when the geometry works out exactly right. Our distant descendants, if any exist, will look up and see an annular eclipse, a ring of sunlight left uncovered, the moon too small to fill the frame. 500 million years ago, the moon hung noticeably larger in the sky. Its orbital distance was somewhat smaller, perhaps 10,000 kilometers closer, and the difference showed. Total eclipses in that era would have lasted longer, the moon's disk taking more time to cross the sun's face. The corona disappeared behind a slightly bigger shadow. Creatures then had no words for eclipse and no instruments to measure the geometry, but they lived beneath a moon that filled a larger arc of sky, one whose tidal grip on the oceans was correspondingly stronger, its pull shaping coastlines that no longer exist. 600 million years from now, the moon will have receded far enough that total solar eclipses from Earth's surface will no longer be possible. The numbers are unambiguous. The moon's apparent diameter will have shrunk below the sun's, and no geometry of alignment will allow it to cover the sun completely. The sky will still hold lunar eclipses. The moon will still rise and set. But that particular wonder, standing in the shadow, watching the corona bloom, will belong entirely to the past. Astronomers in that era, if any exist, will study records of totality the way we study fossils, as evidence of a world that once was. The moon's surface gravity measures about 1/6 of what we feel here on Earth. A rock dropped from waist height on the moon falls with a kind of dreamy reluctance, taking nearly 2.5 times as long to reach the ground. An astronaut standing in full gear weighs no more than a child there. The landscape holds that same unhurried quality. Boulders rest where they landed millions of years ago, undisturbed, nothing strong enough to move them. Without a significant atmosphere, the moon exists in a kind of open silence. Its gravity is too low to hold on to gas molecules for long. They drift away into space rather than accumulating overhead. There is no wind to stir the dust, no weather to speak of, no clouds to scatter the light. The sun rises and sets over a surface that has never heard rain. Shadows on the moon are absolutely sharp, edges crisp as cut paper, because no air softens them. No global magnetic field wraps the moon today. Earth is shielded by an invisible bubble, a magnetosphere that deflects the solar wind and traps charged particles in great arcing belts. The moon has none of that now. Solar particles strike its surface directly, unimpeded, embedding themselves in the topmost layer of dust. It was not always this way. Long ago, billions of years ago, a field did exist. The evidence is still there, locked inside the rocks themselves. Remnant magnetism in lunar rocks carries a quiet testimony. When those rocks solidified billions of years ago, tiny magnetic minerals inside them aligned themselves with whatever field existed at the time, just as iron filings align with a magnet. The field then faded, but the alignment remained, frozen in stone. Geophysicists who have analyzed samples returned by Apollo missions found these ancient signatures preserved with surprising strength. The moon was once a different world, active, dynamic, its interior churning. The lunar dynamo is thought to have shut down somewhere between 1 and 2.5 billion years ago. Though the exact timing remains an open question, geophysicists continue to refine. A dynamo requires a liquid metallic core in motion, convecting, swirling, generating current. As the moon's interior cooled and its core solidified, that motion slowed and eventually stilled. The field did not vanish in an instant. It likely weakened over hundreds of millions of years, fading the way an ember dims when no air reaches it, the glow retreating inward and going out. Let your jaw go loose now. Feel the muscles around your eyes release, the small ones at the corners, the subtle tension above your brow. Your eyelids are heavy in the easiest way, resting where they are, needing nothing. Behind them is a dim and formless space, unhurried, spreading outward as your breathing settles. Each breath makes that inner space a little larger, a little darker, a little more adrift. There is no edge to it. Your face is still. Your breath is low. You are already drifting. Water ice exists in permanently shadowed craters near the moon's poles. Sunlight never reaches the floors of these deep depressions. The sun always rides low on the horizon near the lunar poles, and the crater walls block every ray. Inside, temperatures hover near -170 degrees Celsius year-round. In that sustained cold, ice delivered over billions of years has simply stayed. It accumulates in the dark, layer by layer, each deposit preserved in a cold that never breaks. Planetary scientists working through data from orbital missions in the 1990s and 2000s found strong evidence suggesting these polar ice deposits arrived incrementally, carried by comets and asteroids over the long course of lunar history. Each impactor would have brought a small payload of volatile material. Most of it may have escaped, but some fraction, reaching the poles, slipped into shadow and stayed. Billions of years of accumulation, one delivery at a time. The moon's cold, dark places became archives of the solar system's icy wanderers. Regolith covers the entire lunar surface, a layer of pulverized, fragmented rock, ground down over billions of years of impact after impact. No plate tectonics churn it under. No rain weathers it away. It simply accumulates, centimeter by centimeter, each new impact adding to what was already there. The texture of this material is unlike anything on Earth, fine and abrasive at once, with jagged edges that never wore smooth because there was no water, no tumbling stream to round them. It sits in perfect stillness, undisturbed for millions of years at a stretch. The sun constantly streams charged particles outward in all directions, and on the moon, with nothing to deflect them, those particles sink directly into the regolith surface layer. Over vast stretches of time, hydrogen, helium, and other solar elements have built up inside the grains of lunar dust, grain by grain, year by year. Researchers have used these deposits as a kind of diary of the sun's past behavior, reading changes in composition across depth, like pages in a very old book. The moon's dust has been listening to the sun for 4 billion years, and it remembers. Helium-3 accumulates inside the lunar regolith, deposited grain by the solar wind over billions of years. On Earth, this isotope is extraordinarily scarce. Our magnetic field and atmosphere deflect the solar particles that carry it before they ever reach the ground. The moon, exposed and unshielded, has gathered it in abundance. Every cubic meter of lunar soil holds a quantity that would take vast industrial effort to collect on Earth. It sits there, locked inside the dust, a quiet inheritance from the sun. Across a single lunar day and night, the surface swings through 300 degrees Celsius of difference, from minus 173 degrees in the long lunar night to plus 127 degrees when the sun beats directly down at noon. No atmosphere softens this range, no ocean absorbs the heat. The rock simply bakes, then freezes, then bakes again. It is one of the most extreme thermal environments in the inner solar system, repeated endlessly in 2-week cycles across every exposed plain and ridge. Moonquakes are real. The Apollo missions left seismometers behind on the lunar surface, and those instruments recorded tremors for years after the astronauts departed. The moon shakes, not with the deep rumbling energy of Earth's plate boundaries, but with its own quieter and distinctly alien character. The seismometers sent their readings across space to researchers waiting on Earth, confirming that the moon is not geologically inert. It trembles. The records accumulated over years, a long, slow conversation between the moon and the instruments left to listen. Shallow moonquakes are among the more surprising discoveries from the Apollo seismic record. They can reach magnitude 5.5, comparable to a moderate earthquake, and, stranger still, they can last up to 10 minutes. An earthquake of similar magnitude typically exhausts its energy in under a minute. The moon, being cold and dry throughout much of its interior, does not absorb seismic energy the way Earth's wet, fractured crust does. The vibrations ring on, bouncing through rigid rock, long after their source has gone still. Deep moonquakes originate far below the surface, at roughly 700 kilometers depth, near the boundary between the lunar mantle and a partially molten zone. Tidal forces from Earth are what trigger them. As the moon moves along its elliptical orbit, its distance from Earth changes, and the gravitational pull on its interior fluctuates in a regular rhythm. That rhythm squeezes and releases the deep rock, generating tremors on a predictable schedule. Earth, in a sense, reaches across space and rings the moon from the inside. Tidal stress does more than trigger deep tremors. It also causes the moon itself to flex very slightly as it travels its elliptical path. When the moon is closer to Earth, gravity squeezes it a little more. When it is farther, the grip relaxes. The whole body stretches and compresses by a small but measurable amount with each orbit. This flexing happens over the course of days, too gradual to feel, too subtle to see, yet real enough for instruments to detect. The moon breathes, almost, a long, slow deformation in rhythm with its own journey. Breathe in and let it go. Let the exhale be a little longer than the last one. There is no particular length it needs to be. Just let it stretch out on its own, the way water finds its level without effort. Each breath out is a small release. Your chest drops a little more. Your shoulders settle. The next inhale comes without you asking for it, and the exhale follows. Longer again. The rhythm finds itself. You are already drifting, already moving toward the rest that was always waiting for you. When scientists measure how much the moon flexes under tidal stress, they express that deformation using a value called the love number. It is a dimensionless ratio, a number that describes how readily a body deforms when a force is applied. A perfectly rigid body has a love number of 0. A fluid body has a higher one. The moon's measured love number tells researchers that the interior is not entirely solid. Something in its deep layers is more compliant than rigid rock. That single number carries an entire portrait of what lies beneath the surface. Beneath several of the moon's large impact basins, the crust hides something heavier than its surroundings, dense concentrations of material left over from ancient collisions and volcanic flooding. These regions, called mascons, pull at orbiting spacecraft with slightly more gravitational force than the terrain around them, tugging their paths in measurable ways. Early lunar orbiters in the 1960s began drifting off course in ways mission controllers could not at first explain. The moon's hidden mass was redirecting them, slowly and imperceptibly, as they passed overhead. Two small spacecraft called GRAIL, which stood for Gravity Recovery and Interior Laboratory, flew in formation around the moon in 2012, measuring tiny changes in the distance between them as they passed over regions of varying density. Where the ground below was denser, both craft accelerated slightly, and the gap between them shifted by a fraction of a millimeter. From these minute fluctuations, researchers at the Jet Propulsion Laboratory assembled the most detailed map yet made of the moon's interior structure. The moon gave up its hidden geography to two spacecraft flying in careful lockstep. Crust fault scarps cut across the lunar surface in long, low cliffs, wrinkles pressed into the crust as the moon's interior slowly cooled and shrank over billions of years. As the deep interior contracted, the outer shell had nowhere to go but inward, and where the stress grew too great, slabs of rock slid up over neighboring terrain. Some of these scarps stretch for kilometers, rising a few tens of meters above the surrounding plains. They are the moon's own record of a slow, patient cooling, a world folding in on itself across immense spans of time. Each year that the moon drifts a little farther from Earth, the month grows very slightly longer. The connection is precise and mathematical. A more distant moon moves more slowly in its orbit, just as the outer planets take longer to circle the sun than the inner ones do. Over millions of years, this change accumulates. The moon's month today is 27.3 days. Far in the future, it will be a day longer. Then two, then several, the calendar of the Earth-Moon system rewriting itself one slow orbit at a time. Distance weakens gravity's reach, and as the moon moves outward, Earth's tidal grip on it eases. Tidal force falls off steeply with distance, not just proportionally, but with the cube of that distance, so even a modest increase in the moon's orbit means a measurably softer tug. Earth still reaches across that widening gap, still raises a subtle bulge in the moon's body, still whispers its gravitational influence into the rock and iron below the lunar surface. But the whisper over time grows fainter. One consequence follows naturally from the other. When the tidal squeeze on the moon loosens, the flexing that generates internal heat decreases as well. The moon already runs cold. Its interior has been cooling for billions of years, but tidal flexing from Earth's gravity has contributed a small, steady trickle of warmth deep within the rock. As that flexing diminishes, even that faint internal heat source fades further. The moon's deep interior grows a little more still, a little more settled. The ancient restlessness of its formation recedes another step into memory. Planetary scientists working with long-term tidal models expect the moon's outward drift to slow its own pace over geological time. As the tides that drive the recession become weaker, they push less efficiently, and the moon inches outward at a slightly reduced rate. The current rate, about 3.8 centimeters per year, is likely higher than the average across deep time. The future rate will be lower still. The moon will not stop moving outward, but it will do so with ever less urgency, easing into the long remainder of its journey. Over the next 250 million years, the continents now scattered across the globe are expected to converge again. Plate tectonics works on its own unhurried schedule, opening oceans in some places while closing them in others. Geologists have named several competing models for what this next supercontinent might look like. Amasia, Orica, Nova Pangaea, each describing a different arrangement of the land. Whatever its shape, a vast landmass will again gather the continents into one body, reshaping the planet's face as dramatically as any event in its long history. A single great landmass changes the oceans in ways that ripple all the way to the moon. When continents are fragmented and spread apart, shallow inland seas and narrow channels amplify the tides. The geometry of the water body matters enormously for how much energy the tides dissipate. With one supercontinent, that geometry shifts again. A deep, unbroken ocean surrounding the landmass would behave differently from today's arrangement, altering the rate at which Earth loses rotational energy and, by extension, altering how efficiently the moon is pushed outward. Let your arms rest where they are. Notice the weight of them. Your hands are heavier than you might have expected. Simply lying there, they press into the surface beneath you with more gravitational pull than you usually feel. Your legs, too, each one rests fully, without effort, the muscle no longer holding anything up. Your back spreads a little wider into the mattress. Your hips settle. The heaviness is not discomfort. It is the body finally acknowledging that it no longer needs to hold itself together. Limb by limb, the effort releases. The weight is the rest. Continental rearrangement will not affect the moon's recession in a single dramatic shift. The change will be spread across tens of millions of years as the supercontinent assembles and the ocean geometry gradually transforms. During periods when tidal dissipation is higher, the moon will recede a little faster. During periods when it is lower, the pace will ease. The moon's outward drift has always been uneven in this way, responding to the slow choreography of the continents below. The future will be no different, a variable tempo within the same long, inevitable movement. 500 million years from now, a person standing on Earth, if any such person existed, would look up at a moon that appears measurably smaller than the one we see tonight. The numbers are clear. 500 million years of recession, at even a reduced average rate, add up to a moon sitting thousands of kilometers farther away. The disk in the sky would be diminished. The tides along every shore would pull with less force. The month would be longer than it is today. The world and its companion will have drifted, imperceptibly but persistently, into a new relationship. Our sun is not a fixed, unchanging lantern. Nuclear fusion at its core has been burning steadily for 4.5 billion years, and as it does, the core contracts ever so fractionally, growing hotter, pushing the outer layers to radiate more energy outward. The brightening is measured at roughly 1% every 100 million years, so gradual it is entirely imperceptible across a human lifetime, or even across the whole span of recorded history. Yet over the vast stretches of geological time, this slow accumulation of heat transforms everything. 500 million years from now, the sun will shine with about 5% more luminosity than it does today. That number sounds modest, written down, a 5 in 100. But across a planet's entire surface, receiving that energy every hour of every day, the accumulated effect is enormous. Earth's atmosphere, its oceans, its rock cycles have all been tuned by evolution and geology to the sun it receives right now. A 5% increase tips many of those finely balanced systems into new territory, shifting the climate in ways that cannot easily be undone. Earth has a long-running thermostat built into its geology, called the carbonate-silicate cycle. Carbon dioxide in the atmosphere dissolves into rainwater, weathers silicate rock, and carries carbon into the ocean, where it eventually gets locked into limestone on the seafloor. Tectonic activity then returns that carbon to the atmosphere through volcanic outgassing. This cycle has kept Earth's climate broadly livable for billions of years. But it was calibrated for the sun's current output. As solar luminosity rises, that calibration begins to slip. The cycle comes under stress. It was never fully designed to absorb. Carbon dioxide levels in Earth's atmosphere will fall dangerously low somewhere between 500 and 600 million years from now. As the planet warms under a brighter sun, the chemical weathering of rocks accelerates, pulling more carbon dioxide out of the air and into the ground faster than volcanoes can replenish it. The atmospheric concentration drops. Today, Earth's air holds enough carbon dioxide to sustain a rich and complex biosphere. In that distant future, the reservoir will have been drawn down toward the threshold, where the chemistry of life itself begins to fail. The collapse of what biologists call C3 photosynthesis is expected to follow within roughly 600 million years. C3 photosynthesis is the ancient biochemical pathway used by the vast majority of Earth's plants, grasses, trees, ferns, most crops. It depends on a steady supply of atmospheric carbon dioxide. When concentrations fall below a critical level, that pathway simply cannot function. The reaction stalls. Leaves that have been pulling sunlight and carbon together for hundreds of millions of years will find the raw material gone. The forest will have no way to breathe. Most plant life on Earth is expected to go extinct within about 800 million years. This is not a sudden catastrophe, but a slow, deep unraveling, species by species, ecosystem by ecosystem, as carbon dioxide thins and heat accumulates. The planet that nurtured ferns and forests and flowering trees for hundreds of millions of years will no longer be able to sustain them. What remains may be microbial life, clinging to niches too small and too specialized to see from orbit. The great green abundance that covers Earth today will have receded into memory written in rock. Earth's oceans, despite all of that biological transformation, are expected to persist for roughly 1 billion more years from now. Water is remarkably resilient. Even as carbon dioxide drops and plants vanish and the surface warms, the oceans will not simply evaporate overnight. They will shrink at the margins, warm at the surface, shift their chemistry, but the deep basins will hold their water long after the forests are gone. The hydrological cycle, evaporation, rain, the slow return of water to the sea, will continue threading through a changed but still liquid world. Through all of that, the fading forests, the shifting atmosphere, the warming seas, the moon will keep moving. Its recession from Earth does not depend on what grows on the surface below. It does not require an atmosphere, or an ocean full of life, or stable carbon cycles. The physics driving the moon outward are rooted in gravity and rotation, the tidal bulge, the torque, the transfer of angular momentum. Those forces operate whether Earth below is a living world or a warm, desiccated rock. The moon's journey is older than biology and will outlast it. A sound reaches you now, low, undirected, neither near nor far. Perhaps it is the building settling around you. Perhaps it is wind tracing the edge of a roofline somewhere outside. It arrives and then recedes, arriving again a moment later, a little softer. You do not need to name it. You do not need to follow it anywhere. Your eyelids have their own weight now. Your jaw has unclenched on its own. The sound comes and goes like something breathing far away. You are warm. Your thoughts are moving the way clouds move when there is no weather to drive them, aimless, unhurried, dissolving at the edges into the dark. 1 billion years from now, the moon will have traveled roughly 38,000 additional kilometers away from Earth. 38,000 kilometers, a number larger than Earth's own circumference, accumulated grain by grain over 1 billion years of tidal friction and orbital drift. The moon that orbited at 384,000 kilometers will sit at something closer to 422,000. The sky will be different. The tides will be different. The night will be fractionally darker when the moon is full. All of it the result of the same small force, patient beyond any reckoning, pressing outward across time. That additional distance carries a quiet consequence for time itself. The moon's orbital period, the span required for one complete journey around Earth, will have stretched to approximately 29 to 30 days by 1 billion years from now. Today, that orbit takes 27.3 days. The difference seems modest, barely more than 2 days added across 1 billion years of gradual recession. Yet it reflects the deep logic of orbital mechanics. The farther a body travels from the center of its orbit, the more ground it must cover, and the longer each loop takes. Earth's own rotation will have wound down further by that same billion-year horizon. A single day, one full spin of our planet, will last approximately 25 to 26 hours. The mechanism is the same tidal friction that drives the moon outward. Each ocean tide raised and released bleeds a fraction of Earth's rotational energy. 4.5 billion years of this has already stretched the day from 6 hours to 24. Another billion years will add roughly 1 to 2 more. The planet will be spinning, still blue, still tilted, but measurably slower. When both the day and the month grow longer, their ratio shifts. Today, roughly 27 Earth days fit inside 1 lunar month. In 1 billion years, with days running 25 to 26 hours and months stretching to 29 or 30 days, the number of days in a lunar cycle will be noticeably different. The calendar of tides, of moonrise and moonset, of the rhythms organisms have used to time their reproduction and migration, all of it will have recalibrated. Not dramatically, but measurably, undeniably, the relationship between day and month will have moved. Weaker tides will wash Earth's shores in that distant era. Gravity's reach falls off sharply with distance, specifically as the inverse cube, so even a 10% increase in the moon's separation translates to roughly a 27% reduction in its tidal force on Earth. Coastlines will still feel the pulse of rising and falling water, but the difference between high and low tide, that slow vertical breathing of the sea, will be noticeably shallower. The ocean will still move. It will simply move less. Reduced tidal forcing carries consequences below the surface as well. Today, tidal currents churn the ocean's layers, pulling cold, nutrient-laden deep water upward toward the sunlit surface, a process oceanographers call tidal mixing. In 1 billion years, with the moon farther away and tidal forces diminished, that vertical churning will weaken. The ocean's layers will sit more still, more stratified. Deep water will not rise as readily to meet the light. The sea's interior will grow quieter, less disturbed, and in some ways more separate from the world above. Nutrients cycle through the ocean in part, Because tidal mixing carries phosphorus, nitrogen, and iron from the deep toward the photic zone, the sunlit layer where photosynthesis is possible. Planetary science frames this as a question of ocean productivity. If that upwelling weakens, the organisms that depend on nutrient-rich surface water, phytoplankton, zooplankton, everything built upon them, face a changed foundation. Astrobiologists note that ocean stratification, without tidal mixing, may reduce overall marine biological productivity. Quieter seas, in this sense, may mean a less nourished sea. The Sun, too, is changing on this timescale. Main sequence stars grow gradually more luminous as they age, because hydrogen fusion in their cores converts mass to energy, raising the core's temperature over billions of years. By 1 billion years from now, the Sun will be roughly 8 to 10% more luminous than it is tonight. That increment sounds modest, but applied across the full disk of a star, projected over a planet's entire surface, 8 to 10% more energy is a significant addition to Earth's heat budget. More luminosity from the Sun means more energy arriving at Earth's surface. Astrophysicists tracking Earth's long-term thermal evolution describe this as a slow accumulation of surplus warmth. Glaciers will have no purchase in such a world. Ice caps, if any remain, will have retreated to the poles or vanished. The atmospheric circulation patterns that today carry moisture from tropics to mid-latitudes will have reorganized around a warmer, more energetic system. Earth will not look the same from space. The familiar blue-white marble, threaded with cloud, will be carrying more heat in every layer. The result for Earth's surface temperature is striking. Planetary climate modeling suggests, and the models remain genuinely uncertain here, depending on atmospheric feedback assumptions, that Earth's average surface temperature could reach somewhere between 50 and 70 degrees Celsius by 1 billion years from now. That is not the average temperature of a comfortable afternoon. It is the temperature of a pressure cooker. The surface of Earth in that era may sit above the threshold at which liquid water survives under open air conditions, at least at lower elevations. Let the mind drift now. There is no urgency left in the body. Notice the warmth gathering at your palms, not heat, just the easy temperature of skin that has finally stopped working. It moves up through the wrists, following the slow current of the blood, spreading into the forearms, the elbows. The shoulders carry it now. There is a heaviness in the chest that is not worry but rest, the body releasing what it held. Warmth pooling in the jaw, behind the eyes, at the crown of the head. Everything is settling, degree by degree, into the dark. Liquid water oceans on Earth may be nearing their end, approximately 1 billion years from now. The process would not be sudden. Over millions of years, rising temperatures would accelerate evaporation faster than the water cycle could return moisture to the surface. Oceans would thin. Shallow seas would retreat inland and vanish first, leaving pale mineral flats behind. Eventually, the deep basins themselves would grow too warm to hold water under open skies. The blue that has defined this planet for 4 billion years would finally be fading. The habitable zone around the Sun will have shifted outward by 1 billion years. As the Sun brightens, the band of orbital distances where liquid water can exist on a planet's surface moves steadily away from the star. Planetary scientists describe this migration as gradual but relentless, the zone drifting outward at a pace tied directly to the Sun's rising luminosity. Earth sits near the inner edge of today's habitable zone. 1 billion years from now, it will have crossed that inner boundary, leaving it behind. Mars may technically enter the Sun's habitable zone around 1 billion years from now. Today, Mars is cold and dry, orbiting just beyond the outer edge of the region where liquid water could pool on a surface. But as the Sun's habitable zone migrates outward, Mars drifts into alignment with it. Planetary scientists note that the planet itself will not warm automatically. A thin atmosphere and low surface pressure remain formidable obstacles. Still, the geometry will have shifted. Mars will occupy the position in the solar system that Earth holds tonight. The Moon's surface will look almost identical to today after 1 billion more years. No rain erodes it, no wind reshapes it, no tectonic forces buckle or fold it. The highlands will carry the same pale gray texture. The dark volcanic plains will hold the same ancient shapes. The crater that formed 3 billion years ago will still sit where it landed. From a great distance, from a spacecraft approaching in that far future, the Moon will appear as familiar as it does tonight. Geology, on an airless world, is extraordinarily patient. Impact cratering will have added a thin new layer of craters to the lunar surface over 1 billion years. The inner solar system is not entirely empty. Small asteroids and comets still move on, crossing orbits, and occasionally one finds the Moon. Over 1 billion years, the statistical accumulation of these strikes will leave a faint new population of craters scattered across the landscape. Most will be small, tens of meters across or less. They will not erase what is already there. They will simply arrive, one by one, across the long silence, writing their quiet record into the dust. Micrometeorite gardening will have churned the top centimeter of lunar regolith over 1 billion years. Tiny particles, grains of dust and sand-sized fragments, rain down on the Moon constantly from interplanetary space. Each impact is small, but across 1 billion years, the accumulated effect is a slow mechanical mixing. The uppermost layer of soil is turned and retoured, grain by grain, in a process geologists call gardening. The Moon's surface remains still in every sense a human eye could detect, but at the scale of millimeters, it has been quietly stirring the whole time. The Moon's polar ice deposits may persist or grow over 1 billion years depending on solar conditions. Tucked inside permanently shadowed craters near the poles, ice sits in regions where sunlight has never reached for billions of years. Whether that ice survives another billion depends partly on how the sun's brightening affects the Moon's thermal environment, and partly on whether new cometary or asteroid deliveries continue to replenish it. Planetary geochemists acknowledge the question remains open. The ice may thin, it may hold, or, if shadowed conditions remain undisturbed, it may even accumulate further. The Moon's reflectivity will remain similar over 1 billion years. Albedo, the fraction of sunlight a surface reflects, depends on composition and texture. The Moon's surface is made of minerals that have been exposed, irradiated, and space-weathered for billions of years already. Over the next billion, those same processes continue, but they will not dramatically alter the overall brightness. The Moon will still return roughly 12% of the sunlight that falls on it. Seen from a darkened Earth, it will still rise as a pale disk, still cast the same faint silver light across whatever surface remains below. The Moon will still be in synchronous rotation with Earth in 1 billion years. Tidal locking, once achieved, is not easily undone. The same gravitational coupling that brought the Moon's rotation into alignment with its orbit billions of years ago will continue to hold it there. The Moon will still show the same face to Earth. The far side will remain forever turned away, as it has been for most of the Moon's existence. Some things in the universe, once settled into equilibrium, simply remain. The Moon's patient single face toward Earth is one of them. The lunar Maria, those dark volcanic plains, will remain geologically unchanged over 1 billion years. Formed between 3 and 4 billion years ago, when lava flooded ancient impact basins, the Maria have been geologically inert ever since. No new magma moves beneath them. No subsidence reshapes their floors. The basalt that cooled into those plains has been sitting undisturbed. losing heat at the pace of a world already nearly frozen inside. 1 billion years from now, the Sea of Tranquility will still be there. The same dark expanse, the same ancient flow, still and enduring. Let your breath slow now, just a little. Watch it move like dust in still air, a small cloud rising, then settling, then gone. Each exhale carries something away, the weight of the hour, the hum of the day. The dust drifts down, the air thickens into quiet. There is nowhere you need to arrive. The settling continues on its own, without effort, without direction, the way dust always finds its way to rest. Cosmic ray exposure will continue to alter the surface chemistry of the Moon over 1 billion years. High-energy particles streaming in from distant corners of the galaxy have been striking the lunar surface for 4.5 billion years already. They split molecular bonds, create new compounds, darken minerals in a process called space weathering. Over the next billion years, this slow chemical rewriting continues, one particle at a time, layer by layer, building a record no geologist will ever read. Deep inside the Moon, the small iron core has been losing heat for billions of years. At roughly 330 kilometers across, modest even by lunar scale, it began cooling the moment the Moon itself solidified from its ancient magma ocean. By 1 billion years from now, geophysicists expect that core to be more fully solidified than it is today. Its remaining liquid fraction shrunk further still. A tiny iron sphere, frozen in the dark, at the center of a world that has long since gone still. Any residual internal heat in the Moon will be nearly exhausted within 1 billion years. That heat is the last warmth from two sources: the original energy of formation and the slow decay of radioactive elements locked in the deep rock. Both are running down. Radioactive isotopes that once generated gentle warmth have been decaying for 4.5 billion years, and their supply is nearly spent. 1 billion years from now, the Moon's interior will be thermally indistinguishable from the cold of the surrounding space. Geologically, the Moon will be completely dead in 1 billion years. No magma, no volcanic gases, no seismic tremors of internal origin. Even the deep moonquakes, those faint shudders triggered by Earth's tidal pull, measured by Apollo seismometers, will have weakened as the Moon moves farther from Earth and its tidal flexing diminishes. What remains will be a world of total stillness, not sleeping, not waiting, simply a sphere of cold rock, orbiting in silence, its interior story fully told. Escape velocity from the Moon's surface is 2.38 kilometers per second, the minimum speed any particle needs to leave the Moon entirely and never return. That is a relatively low bar compared to Earth, yet it still far exceeds the thermal speeds of most gas molecules in sunlight. Most atmospheric gases, nitrogen, oxygen, carbon dioxide, move too slowly to escape immediately, but solar wind bombardment and ultraviolet radiation steadily strip them away over time. The result is permanent atmospheric loss. No gas lasts long in lunar orbit. 1 billion years from now, the Moon will still have no meaningful atmosphere. This is not a condition that will change with time. It is a permanent feature of the Moon's nature. Its low mass means low gravity. Low gravity means any atmosphere that forms quickly disperses into space. Volcanic outgassing once supplied thin, transient envelopes of gas, but volcanism is now extinct. No internal or external source will replace what the solar wind has carried away. The Moon moves through space bare, unchanged in this regard, as it has for most of its existence. Over long stretches of time, the Moon's orbital inclination and eccentricity do not stay perfectly fixed. Solar gravity tugs at the orbit from a different angle than Earth's does. The other planets, millions of kilometers away, add their own faint but real influences. The result is a slow oscillation, the Moon's orbital tilt and shape wobbling gradually, like a plate spinning on a table as it settles. These variations are small and predictable, and they unfold over timescales of thousands to millions of years, a rhythm too slow to notice, too steady to ignore. Jupiter and Saturn, the two largest planets in the solar system, exert gravitational perturbations on the Moon's orbit that play out over millions of years. Their combined mass is enormous. Jupiter alone holds more than twice the mass of all other planets together. From their distant orbits, they shift the positions of planetary bodies throughout the solar system through a slow gravitational conversation. The Moon is not immune. These far perturbations arrive quietly, barely a whisper of force at any given moment, but accumulated over geological time, they shape the orbit's long-term behavior. A mechanism studied by Soviet physicist Mikhail Lidov in the early 1960s and independently by Japanese astronomer Yoshihide Kozai describes how a distant third body can, in principle, cause large oscillations in a smaller object's orbital inclination and eccentricity over time. Applied to the Moon, the Lidov-Kozai mechanism is thought to be largely suppressed by Earth's strong gravitational dominance over its satellite. Orbital dynamicists note that as the Moon recedes, Earth's relative hold weakens slightly, and whether the mechanism could become meaningful on timescales far beyond 1 billion years remains an area of continuing study. Recession changes the balance of forces. As the Moon moves farther from Earth, the Sun's gravitational pull does not diminish, but Earth's hold over the Moon does in relative terms. The result is that solar perturbations on the Moon's orbit grow stronger over time. Each centimeter of outward drift tips the balance slightly further toward the Sun's influence. It is a gradual shift, unfolding across millions of years, but it is real and measurable in the long-term architecture of the orbit. Let your jaw go slack now. Feel the small muscles around your eyes release, the ones that held the day's expressions, the ones that tensed without your asking. Behind your closed eyelids there is nothing but dim, easy dark. That space is yours. Your face softens by degrees, as if setting down something it had carried for hours. The heaviness behind your eyes is not tiredness, it is arrival. Rest is already here, already holding you. Drift carries consequences. With every passing million years, the Moon's orbit grows wider, and the Sun's gravity accounts for a larger fraction of the forces acting on it. Earth remains dominant. The Moon is still firmly in its keeping, but the Sun's relative influence rises with distance. Planetary dynamicists who study this evolution describe it as a slow gravitational rebalancing, one that will not destabilize the Moon in any near-term future, but will subtly reshape the orbital environment over the billions of years ahead. Every planet holds a region of space in which its own gravity dominates over the Sun's pull. This region is called the Hill sphere. For Earth, that boundary sits at roughly 1.5 million kilometers, a vast bubble of gravitational authority extending far into space. Within this sphere, moons and other objects can maintain stable orbits around Earth without being stolen away by the Sun. The concept was formalized in the 19th century by American astronomer George William Hill, whose mathematical work gave this region its name. Earth's moon orbits at roughly 384,000 kilometers from home. The Hill sphere boundary lies at 1.5 million kilometers. By that measure, the Moon sits well inside the protected zone, about 1/4 of the way to the edge. The Sun's influence, however real, does not come close to overwhelming Earth's grip at this distance. The Moon rests in a position of deep orbital security, held comfortably within the gravitational territory that Earth has claimed from the surrounding solar system. Even as the Moon drifts outward through the coming billions of years, it will remain well within the helisphere's embrace. A full billion years of recession adds roughly 38,000 kilometers to the Earth-Moon distance, a meaningful shift in astronomical terms, yet still placing the Moon at less than 30% of the way to the boundary. Stability is not merely likely here. It is the natural and expected state, barring disruptions that current models give no reason to anticipate. Numerical simulations run on modern computing systems have traced the Moon's orbital path forward across 1 billion years, accounting for the gravitational forces of the Sun, Earth, Jupiter, Saturn, and the other planets. These calculations, some carried out by teams at institutions including the Paris Observatory, find the orbit stable. It oscillates, it breathes in and out with small variations in shape and inclination, but it does not escape. The broad arc of 1 billion years, in simulation after simulation, ends with the Moon still orbiting Earth. Chaotic behavior is a known feature of gravitational systems with many interacting bodies. Orbital dynamicists note that beyond 1 billion years, resonances between the Moon's orbit and the motions of Earth or the other planets could, in principle, accumulate into unpredictable perturbations. These would not necessarily cause the Moon to escape, but they could drive changes in orbital eccentricity or inclination that depart from current projections. The precise state of the Moon's orbit 2 or 3 billion years from now is genuinely uncertain. No current simulation can fully resolve that distant horizon. Far enough into the future, the story of the Moon becomes inseparable from the story of its star. Beyond 1 billion years, the Sun itself will begin to change. Its core will exhaust the hydrogen fuel that has sustained it for billions of years. Its outer layers will respond by expanding. The conditions that have governed the Earth-Moon system, the familiar orbits, the tides, the slow recession, all of these exist within a window that the Sun's evolution will eventually close. The Moon's long-term fate is a chapter in a larger stellar story. Roughly 5 billion years from now, the Sun will exhaust the hydrogen at its core and depart the phase of its life that astronomers call the main sequence. It will begin to expand, its outer layers swelling outward over hundreds of millions of years into what is known as a red giant. This transformation is not sudden. It is an aging, drawn out across timescales longer than Earth has yet existed. 5 billion years is more than the current age of the solar system. It is a vast distance of time, and the Moon and Earth will have changed enormously before that moment arrives. When the Sun enters its red giant phase, the inner solar system will be transformed beyond recognition. Mercury and Venus will be swallowed entirely, their orbits consumed by the expanding stellar atmosphere. Earth and the Moon, orbiting farther out, will not be engulfed, but they will be scorched by a luminosity hundreds of times greater than today. The surfaces will be stripped and baked. The oceans, long since gone, will leave no trace. Long before the Sun reaches that stage, tidal evolution will continue pulling Earth and Moon toward a mutual tidal lock. Both bodies would, given enough undisturbed time, reach a state where each keeps the same face perpetually turned toward the other. Two worlds frozen in a slow gravitational embrace, each the permanent horizon of the other. The physics points clearly in that direction. The trajectory is set. Only time is the question. Breathe in and feel the air fill you to its fullest depth. Then let the exhale come, not forced, just released, like something you were holding without knowing it. The next breath finds its own way in, and the next exhale takes just a little longer, a little lower. Each breath is a small tide, rising and falling, with no effort from you at all. You are already doing the only thing there is to do. The breath continues on its own. Achieving full mutual tidal locking between Earth and the Moon would demand an enormous span of time, far greater than what remains of the Sun's stable, hydrogen-burning life. Calculations by tidal evolution researchers place the timescale for complete Earth locking at well over 50 billion years, more than 3 times the Sun's remaining main sequence lifetime. The universe is old, but not old enough for this particular ending. The Sun will intervene long before the dance completes. At the end of that long tidal road, if nothing interrupted the process, Earth's rotation would slow until one full day lasted the same duration as the Moon's orbit, approximately 47 times the length of a current day. The Moon would hang fixed above one hemisphere, motionless in the sky. The opposite hemisphere would never see it at all. Days and months would have merged into a single enormous interval of time, vast and unhurried beyond any human measure. That tidally locked endpoint will never arrive. The Sun's transformation into a red giant will occur billions of years before Earth's rotation slows enough to complete the lock. The 47-day equilibrium is a destination the Earth-Moon system is traveling toward, but will never reach, a mathematical horizon that recedes ahead of the journey. The solar clock runs out first. The story of tidal locking ends not with completion, but with the closing of the chapter by a larger event. Tidal evolution between Earth and Moon is, in the deepest sense, an unfinished story. The forces are real, the direction is clear, and the physics is well understood, but the process will be overtaken by stellar evolution before it ever resolves. What we observe today is a system mid-transformation. Earth still spinning too fast, the Moon still drifting outward, the tidal forces still at work, all of it paused, in the long view, by the lifespan of a star. To describe where the Moon will be in 1 billion years, astronomers use a single precise number, the orbital semi-major axis. This is the defining measurement of an orbit's size, not the Moon's position at any given moment, but the average of its closest and farthest distances from Earth. It distills the entire shape of the orbit into one clean value. When that number changes, the orbit has changed. The semi-major axis is the address of the Moon in space. The semi-major axis of the Moon's orbit today measures 384,400 kilometers, a number refined over decades of lunar laser ranging with millimeter precision. It is the baseline from which all projections of the Moon's future are made. Every year, that number grows by about 3.8 centimeters. Over 1 billion years, those centimeters accumulate into something measurable, something that reshapes the rhythm between our world and its companion. 1 billion years from now, the semi-major axis of the Moon's orbit will have grown to somewhere between 422,000 and 426,000 kilometers. That range reflects the genuine uncertainty in projecting tidal dissipation rates across geological timescales. The Moon will not have fled to an alien distance. It will still be the Moon, recognizably present, still orbiting Earth. But farther, a little more distant. The night sky a little emptier for it. A 10% increase in distance may sound modest, but across the immensity of space it represents a real and permanent shift in the Earth-Moon relationship. The Moon will be roughly 38,000 kilometers farther away than it is tonight, a gap that took 1 billion years of quiet, steady drift to open. No dramatic rupture, no sudden leap. Just the patient accumulation of 3.8 centimeters per year, year upon year, century upon century, until the distance between our world and its companion has grown by 1/10 of what it once was. Angular diameter, the width of the Moon as measured in degrees across the sky, will have decreased by roughly 8 to 9% over that same span of time. An 8% reduction is not catastrophic. The Moon will not become a pinprick, but it will be a measurably smaller disk, the way a lantern looks slightly diminished when carried a few steps farther down a long corridor. The eye that knows the current Moon well enough would notice the difference. The full Moon would be a little less imposing, the shadows it casts on a clear night a little less sharp. Observers standing on Earth in 1 billion years, whatever form of awareness might exist by then, would look up at a night sky holding a moon that is unmistakably present but noticeably reduced. The familiar shape would still be there, the dark plains, the pale highlands, the ancient craters, but the disk would sit a little more modestly in the sky, the way a coin held at arm's length appears smaller than one held close. The night sky itself would feel subtly different, a little more open, a little more dominated by stars. Let your body grow heavy now, not all at once, limb by limb, the way warmth spreads inward on a cold night. Feel the weight of your legs, your feet, the full length of them pressing down into the mattress. Let them be heavy. There is nothing they need to carry. Your arms next, let them go slack. Release the last of the day from your hands, from your fingers. Your shoulders drop. Your back widens and settles. You are not floating. You are held firmly and completely by the surface beneath you. Each breath draws you a little deeper into that stillness. The body knows what to do now. Let it sink. Tidal force is not the same as gravitational pull. It is the difference in gravitational pull across an extended body. Gravity weakens with distance, and tidal force weakens far more steeply. The relationship follows the inverse cube of distance, double the distance, and the tidal force drops to 1/8. Move the moon 10% farther away, and the effect on Earth's tides is not a 10% reduction, but something considerably larger. This steeper scaling is why relatively small changes in orbital distance can carry surprisingly significant consequences for the rhythm of Earth's oceans and its deep interior. Carry that scaling one step further. A 10% increase in the moon's distance translates to a reduction in tidal force of approximately 27%. More than a quarter of the moon's tidal influence on Earth would be gone. The oceans would still rise and fall. Tides would not vanish, but the forces driving them would be measurably weaker. This is the compounding logic of the inverse cube at work, turning a modest drift in distance into a significant change in the mechanical coupling between our planet and its moon. The numbers do not alarm. They simply show the deep interconnection of all things in this system. Earth's axial tilt is held remarkably steady today by the moon's tidal torque, a gravitational steadying hand that has kept our planet from tumbling into extreme orientations. With tidal force reduced by more than a quarter, that steadying hand would be weaker, not absent, but diminished. The moon would still exert influence over Earth's orientation in space. It would still be the largest stabilizing factor our planet possesses, but the margin of stability would narrow somewhat, and the axial tilt might wander across a slightly wider range than it does today. Planetary scientists have explored what a slightly wider axial wandering might mean over the long term. The models suggest that Earth's tilt could drift across a somewhat broader band, perhaps a few tenths of a degree to a degree or two more than the current variation of about 2.4 degrees. That is modest. It would not produce the extreme oscillations that Mars experiences. The wandering, if it occurs, would be slow and gradual, a gentle broadening of the range, not a dramatic tumble. But even small axial shifts, compounded over millions of years, leave marks on climate. Climate, over geological time, is sensitive to the angle at which sunlight falls on the planet. Axial tilt variations alter the distribution of solar energy between the poles and the equator, shaping ice ages, warm periods, patterns of monsoon and drought. Modest additional variation in tilt, introduced gradually over hundreds of millions of years, could shift the timing and intensity of these long climate cycles. It is an open question how large that influence would actually be, given all the other changes Earth will undergo. The evidence only hints at the scale of the effect. Precession, the slow wobble of Earth's rotational axis across a great circle in the sky, is driven partly by the sun and partly by the moon. The moon contributes the larger share. Its gravitational torque acts on Earth's equatorial bulge, the slight outward swelling at the equator caused by our planet's rotation, pulling it toward the plane of the lunar orbit and producing a steady, stately wobble. The full precession cycle currently takes about 26,000 years to complete. As the Moon recedes and its torque weakens, that cycle will lengthen, the wobble will grow more unhurried, the great slow circuit of the pole across the sky a little more drawn out. Precession's pace is not fixed, it shifts with the Moon's distance, and as the Moon moves outward over the coming billion years, the wobble of Earth's axis will slow. The current cycle of 26,000 years will stretch, unhurried, perhaps reaching 28,000 years or beyond. A longer precession period means the pole traces its great circle across the sky more gradually, each full loop taking a longer breath to complete. It is a deepening of the rhythm already in motion. Earth's great ice age rhythms, the Milankovitch cycles, depend partly on the pace of precession. A longer precession period shifts the timing of when each hemisphere faces the Sun at different points in Earth's elliptical orbit, altering which seasons are milder and which more extreme. The eccentricity and obliquity components of the Milankovitch cycles are also linked. Over millions of years, a slower precession would nudge the pattern of glacials and interglacials into a different cadence, not erasing them, but retuning their intervals like a clock whose mainspring has been slightly loosened. Glacial cycles, a billion years from now, will carry the imprint of a more distant moon, longer, differently spaced, tuned to a precession that has slowed and an obliquity variation that has widened somewhat. The periodicity of ice ages, already shaped by the 100,000-year and 41,000-year rhythms we recognize today, will have shifted. Cosmologists who study deep-time climate acknowledge that predicting the precise cadence that far ahead is beyond current models. But the broad shape of the change is understood. A moon farther away means Milankovitch cycles running on a different clock. The moon's recession also touches something more subtle, the wandering of Earth's poles across its own surface. Polar wander, the slow drift of the geographic poles relative to the underlying mantle, is driven by shifts in how mass is distributed across the planet. The moon's tidal torque contributes a modest component to this process. As the moon recedes, that component changes slightly. Geophysicists who study true polar wander note that the moon is one factor among several, but a measurable one. Over a billion years, even a modest change in that influence would allow the poles to drift along a somewhat different path. Somewhere far off, a sound arrives, low and formless, the way a house settles in the deep hours, a creek dissolving into silence. Then another, further away. You are not listening for anything. The sound comes and goes on its own. Your body is already heavy, already slack, sinking into whatever holds you. The distant settling continues, unhurried, aimless, and you let it move through the room without following it. Breath in, breath out. The house breathes around you, and you are at rest inside it. Plate tectonics, the great grinding drift of continents that has reshaped Earth's surface for billions of years, may not continue indefinitely. The engine driving it is Earth's internal heat, a diminishing inheritance from the planet's formation and the ongoing decay of radioactive elements in the mantle. Within 1 to 2 billion years, as that heat bleeds away into space, the mantle may stiffen and cool enough that the plates slow and eventually stop. Geophysicists debate the precise timeline, but the direction is understood. A cooling interior will eventually bring the slow dance of the continents to rest. Carbon dioxide, the quiet regulator of Earth's long-term climate, depends on volcanic outgassing to stay present in the atmosphere. Volcanoes release carbon dioxide that would otherwise be locked in the rock cycle forever. When plate tectonics slows, volcanic activity diminishes alongside it, and the outgassing of carbon dioxide drops. The carbonate-silicate cycle, which has kept carbon dioxide at livable levels for billions of years, requires the active churning of the crust to function. Without that churning, the replenishment of atmospheric carbon dioxide would slow to nearly nothing. When volcanic outgassing fades, Earth loses its long-term carbon dioxide replenishment while rocks and oceans continue drawing the gas down. The result is an accelerating depletion of atmospheric carbon dioxide, faster than it would decline if plate tectonics were still active. The collapse of photosynthesis, already expected around 600 million years from now for most plants, would arrive sooner or more completely under a tectonically dormant Earth. A once-living world would find its two great life support systems, a warm moon-stabilized climate and an active carbon cycle, both dimming at roughly the same moment in deep time. 4.5 billion years ago, the moon was born, and from that first moment, it became woven into the conditions that allowed Earth to become habitable. It steadied the axial tilt, it stirred the tides, it slowed the day to a livable length. Over the coming billion years, every one of those contributions will have diminished, the tides weaker, the stabilizing torque reduced, the day lengthened, the precession rhythm altered. The moon will still be there, still orbiting, still shining, but its role as a shaper of life's conditions on Earth will have quietly, gradually wound down. Through all of this, the receding orbit, the lengthening month, the shifts in tides and climate and axial wobble, the moon will not collide with any other large body in the solar system within the next billion years. Its orbit is stable, well within Earth's gravitational domain, and the paths of the other planets and their moons do not cross it. The moon will drift outward along its prescribed arc, year by year, century by century, unhurried and intact. Whatever else changes in the far future, this will not. The moon will still be there, circling Earth, as it has always done. No known asteroid or comet trajectory threatens to significantly alter the moon's orbit in 1 billion years. The solar system has been mapped with remarkable thoroughness, and every catalogued body of meaningful size moves along paths that do not cross the moon's domain in any threatening way. The orbits of asteroids and comets are monitored, modeled, and projected forward. None of them reach far enough, at the right angle, with enough mass to nudge the moon off its long, unhurried arc. The moon's future, in this regard, is as open and unobstructed as a field at dusk. Tidal dissipation governs the moon's orbital evolution, and because it does, that evolution is predictable. Tidal forces follow well-established physical laws. The same equations that describe ocean tides today also describe, with patience and precision, the moon's position a billion years from now. The mechanics are not mysterious. Angular momentum flows from Earth's spin outward into the moon's orbit, step by measured step, century after century. The physics is settled, the direction certain, the arc knowable. There is a deep reassurance in a universe that follows its own rules so faithfully. Models of Earth-Moon tidal evolution draw on two sources: the recession rate measured today by lunar laser ranging, and geological records reaching back billions of years. Scientists compare data from ancient tidal rhythmites, layered sediments that recorded the rhythm of tides in Precambrian seas, with the numbers produced by tidal equations. Where the models match the rocks, confidence grows. Where small discrepancies appear, the models are adjusted. It is a collaboration across deep time, the past speaking to the present, and the present projecting forward into the future. Uncertainty in ancient tidal dissipation rates introduces small errors in long-term moon position predictions. The rate at which Earth's oceans dissipated tidal energy was not constant. It shifted as continents drifted, as seas shallowed, as ocean basins changed shape. Each era had its own tidal character, and we can only read those eras imperfectly through the rocks. The errors compound over a billion years, but they remain bounded. Planetary science has established that these uncertainties accumulate to only a modest fraction of the total predicted displacement. The imprecision is real, but it is manageable. The best current estimates give the Moon's position an uncertainty of a few thousand kilometers over 1 billion years. A few thousand kilometers sounds large, but against the total distance of roughly 422,000 kilometers, it is a small fraction, less than 1% of the whole. The precision achieved here is extraordinary, modeling a moving body across 1 billion years of time and arriving at an answer accurate to within a margin thinner, proportionally, than the width of a finger held against the night sky. The Moon's future location, though not perfectly known, is known well. Warmth moves through you now, in no hurry at all. It starts at the soles of your feet, a low, spreading heat, the way sunlight pools on a wooden floor in the afternoon. It rises into your ankles, into your calves. It does not rush. Each part of you it touches becomes heavier, more settled, more at ease. The warmth reaches your knees, your thighs, your hips, and you feel yourself sinking just a little more into the surface beneath you. Your lower back softens. Your chest opens slightly. The warmth keeps moving, unhurried, thorough, reaching every last corner of you. Your shoulders drop. Your jaw loosens. Even your eyelids feel warmed through. There is nothing to resist. The warmth has found you, and it is staying. Approximately 422,000 kilometers will separate the Moon from Earth 1 billion years from now. Today that distance stands at 384,400 kilometers, a number measured to within centimeters by laser pulses bounced off mirrors left on the lunar surface. The difference between now and then is roughly 38,000 kilometers, an increase of nearly 10%. That gap accumulated over 1 billion years of tidal exchange, grain of momentum by grain of momentum, pulled by the same force that draws the ocean into a bay on a still evening. This distance is calculated by integrating the tidal dissipation equation forward in time. The equation describes how energy leaks from Earth's rotation into the Moon's orbit with every tidal cycle. An integration means summing that leak across every cycle for 1 billion years. It is, at its core, an act of patient addition. Each year adds its small increment, 3.8 centimeters, and over 1 billion years those increments total a gap wide enough to notice from Earth's surface. The mathematics is not exotic. It is the same kind of accumulated patience that builds a mountain from sediment or a reef from coral. At that greater distance, a full lunar orbit will take roughly 29.5 to 30.5 days. Today, the Moon completes one orbit in 27.3 days by the stars, and about 29.5 days as measured by the return of the full Moon. In 1 billion years, the orbit will have stretched, and the Moon will move just a fraction more slowly through its wider circle. The change is modest, measured in hours across 1 billion years of drift. The rhythm of the lunar cycle, so ancient and so woven into the experience of life on Earth, will persist, altered only by the most patient of increments. Earth will rotate once every approximately 25 to 26 hours at that future epoch. A day that long will still feel like a day, sunrise, noon, evening, dark, but each one will carry an extra hour or two that today's world does not know. The change has been accumulating since the Moon first formed, 6-hour days, stretching to 10, to 15, to 24, and onward still. By 1 billion years from now, Earth's rotation will have shed another hour or more of its ancient speed. The planet will turn as it always has, just a little more thoughtfully, a little more at ease with its own motion through space. Farther from Earth, the Moon will cast a slightly smaller gravitational shadow across the oceans. Solid angle is the measure of how large an object appears when you account for its full three-dimensional reach, and a moon 10% more distant subtends a measurably smaller one. That shrinking footprint means the tidal pull, already the most ancient rhythm the oceans know, will ease further. The seas will still answer, the bulge will still form. But its height, its reach, its strength, all will have settled into something a degree or two quieter than today. The moon's position 1 billion years from now is, in the end, a simple summary: farther out, slower in its orbit, and fractionally smaller against the sky. Each of those three qualities flows from the same source, the tidal exchange that has been running, without pause, since the moon first coalesced from molten debris. Farther because momentum carried it outward. Slower because wider orbits demand less speed. Smaller because distance shrinks all things. Nothing mysterious in any of it. Just the long, accumulated consequence of gravity doing what gravity always does. 1 billion years from now, the moon will still exist. It will be a large, cratered, geologically dead world circling Earth in the dark. No oceans on its surface. No wind, no eruptions disturbing its ancient plains. The highlands will stand as they have stood for 4 billion years, pale and still under starlight. The dark Maria will remain where lava pooled and hardened long before complex life first appeared on Earth. The moon will persist, not vibrant, not changing, but present, enduring, a companion in the most steadfast sense of the word. No process known to science will pull the moon from Earth's orbit within the next billion years. Planetary perturbations from Jupiter and Saturn nudge its path in long, slow cycles, but never enough to unravel it. Solar radiation pressure is negligible against a body so massive. The Hill sphere, the zone within which Earth holds the moon against the sun's competing pull, will remain intact. Long-term numerical simulations run forward across 1 billion years of model time, find the orbit stable, returning to itself, looping its wide path around Earth without escape or collapse. Across all that time, the moon will have been recording. Every grain of regolith turned by a micrometeorite, every cosmic ray leaving its faint chemical signature, every crater pressed into the surface by an arriving stone, all of it preserved in silence. The moon has no weather, no erosion, no plate tectonics to erase what has been written. By 1 billion years from now, its surface will hold within it the entire accumulated story of the solar system's middle age, 4.5 billion years of arrivals, of solar outbursts, of the slow dimming of impacts across deep time. From its greater distance, the moon will still light Earth's nights. Moonlight is reflected sunlight, and the moon's albedo will not have changed, so the same fraction of sunlight will bounce back toward Earth as it does tonight. The light will arrive from a slightly smaller disk, and the illuminated nights will be just a shade dimmer than we know. Tides will be gentler, their rise and fall less dramatic along coastlines that may themselves look nothing like the ones we know. But the moon will be there, overhead, casting its silver across whatever surface lies below. The moon's slow outward journey is not a departure. It is a signature, the ongoing record of a tidal conversation that began the moment the moon first formed, when Earth's gravity caught the debris of a collision and held it close. Every centimeter of recession is a sentence in that exchange. Every lengthened day, every weakened tide, every fraction of momentum transferred from spinning Earth to orbiting moon, all of it written in orbital distance, preserved in the motion itself. Tonight, the moon is exactly where 4.5 billion years of that exchange have placed it. And you are here, beneath it, at rest, a small and wondrous part of the same long story. Let your breath settle. Let the weight of the day dissolve into the dark. The moon will keep its vigil. You can sleep now. Good night.